Yes. So today we'll start our discussion on segmentation. So we need to understand what is the segmentation part, how it is different than the previous one, that is the contiguous memory allocation, and what are the advantages of making use of segmentation. Okay. So segmentation actually deals with user's view of memory. Okay, because when, and again here user is the end user. Say for example, programmer is also the end user. So whenever programmer writes the program, now you can think of program not just as a set of instructions, but we have something called as the main function. Different methods are there, procedures are there, objects are there, functions, depending upon what kind of programming language you are using. There will be something like a few common blocks will be there, local variables, global variables, arrays, symbol table, stack. So many things are there. So when we say just program, it is not just a text. Okay. So many things are there, and these are all logical units or components of the program, component of executable file. Wherein, like for example, if I think of C++, then we have something called as a functions, something called as a methods. You may wonder what is difference between function and method. So whenever it comes to object-oriented programming, the member functions are actually called as methods. Maybe common procedures are there, main function is there, classes are there, objects are there. So always think of segment, which is a logical unit, and it could be any one of the things I just mentioned. So for example, if you imagine the program, the user's view of program is something like this. Now in this diagram, you can see there is a main function, main program is there. Then we have a stack memory, different subroutines are there. Maybe SQRT is also mentioned there. It is a standard library function which I want to use. Okay. So in contiguous memory allocation, what we did is whole program once loaded into the memory, the space required is contiguous. Now we want to see the segmentation part. Okay. So in user space, whatever the numbers you can see here, like 1, 2, 3, 4, these are all segments. Imagine something like your code is logically divided in different parts, and these different parts will be loaded into the memory anywhere. Like previously, we need contiguous memory. So imagine something like let me make use of annotation tool here, and suppose this is 2 KB, this is 1 KB, this is 3 KB, and say this segment is something like 5 KB. Now if I add all these sizes, the program needs 5 plus 3, 8, 8 plus 2, 10 plus 1, 11. Total 11 KB is required. And in memory, I need contiguous 11 KB block. Right? That was earlier requirement. And because of fragmentation, we already saw that it is difficult to manage that much space. Right? Now, in the segmentation memory management scheme, what happens is your program will be divided based on logical segments, rather logical parts of your program. Say, for example, here maybe 1 denoting a square root function, 2 denotes main function, 3 could be something else, 4 maybe your global, something like that. And now this memory management scheme allows us to load any segment anywhere. So in total, definitely we need 11 KB, but not contiguous. So that constraint actually we are removing. For example, first segment is loaded first, then fourth segment, then second segment, and then third segment, something like this. So wherever memory is available, segments will be loaded. So it removes the requirement of contiguous allocation. But then we need to understand how a specific logical address will be converted to physical. Reason behind that is when the program was loaded in contiguous single block, given just the base address, virtual address will be simply added into that. We also call that as an relocation address, right? In that case, what happened is the logical address is mapped to physical address by simple addition. Now with the segmentation architecture, remember that logical address will consist now two parts. One is the segment number and second one is offset within that segment. So for example, in previous diagram we have 4 segments. So definitely segment number 1, 2, 3, 4 and offset within individual segment. So that is now the structure of logical address. And then we need to have something called as segmentation table, which will map the two-dimensional physical address with base and limit register. Note that previously we just have base and limit, single pair. Now this time we need base and limit for each segment, and that information will be stored in the segment table. With contiguous allocation, you can think of like single segment. And here we have multiple segments. And because multiple segments are there, we need to keep track of all the segments, right? And this information will be stored in one table called as a segment table. Now, interestingly, this segment table is also there in the memory. Segment table has to be stored somewhere, no? So this table is also stored in the memory, right? Now, for example, in previous case, we'll have segment table with 4 entries in it, 1 entry per segment. Now, in previous diagram we saw 4 segments are there. So my segment table will have 4 entries. There is one question in the chat and it is, sir, what is offset in address? Okay, fine. So offset, we saw that in contiguous allocation also. So for example, offset is something like displacement from the some location. Okay. So for example, suppose there is a building, or maybe you think of labs, like in computer department we have 6 labs, like lab 1, 2, 3, 4, 5, 6. Okay. Now if I am in lab number 2, okay, and now I want to refer you to lab number 4. Now what I can say is next to next, something like that. So from that fixed location, like for it is like a relative distance, displacement rather. Okay, that is what the offset is. And how we have utilized that in a contiguous memory allocation is, my logical address will always start with 0. Say for example, if memory requirement is 11 KB as I mentioned, so my address will start with 0, 1, 2, 3, 4, 5, 6 up to 11 KB. And whenever I need to refer to the address, say for example 5, okay, so 0th address will be stored somewhere and that is given by the base register. And when I say 5th address in logical space, then definitely it will be base address plus 5. Now what is this plus 5? That is the offset. Okay. Exactly same idea we want to replicate here. Only change is it will not be single contiguous space, it will be multiple segments, and these segments will be created not randomly, depending upon whatever the view, logical view of your process is. Like for example, if I have one function, separate function, maybe user defined function, that will be going in separate segment, something like that. Okay. Now two important parts are here. One is called as segment table, and how many entries will be there in the segment table, that depends on how many segments are there for that program, right? And the interesting part I am talking about is this segment table is also stored in the memory. How to locate it then? That is very simple thing. For that, operating system utilizes one register called as STBR, segment table base register. Like it is like relocation register, but relocation register points to the starting address of your process. Here it will point to starting address of segment table. You can imagine this as an array, right? So segment table base register. Like we have base and limit, because if starting address is given to you, you should know where to stop, right? Where to stop. For that, you imagine something like you are passing an array to one of the function in C and C++. When you pass an array, what happens is just starting address will be passed. Where to stop then, right? So in order to stop, we usually pass number of elements in that. On the same line, we pass the segment table base register, and in order to stop, there will be one more register called as segment table length register. Okay, so that will indicate how many records are there in that table. Each record corresponds to single segment, so definitely that will indicate number of segments used by the program. So in the logical address on the top, if you can see it here, in the logical address, this segment number is valid or it is legal if and only if the value of that is, say for example, if it is yes, it is less than STLR. So in previous case where I mentioned 4 segments, if there is a logical address with segment number 7, that is invalid, that is illegal. Why? Because program have just 4 segments. We cannot have 7th segment there, right? So that is the case. And regarding offset, offset is within, that is the length of that particular segment. Like in previous diagram I mentioned, segment number 1 with 2 KB, segment number 2 is with 1 KB. So this 2 KB, 1 KB, 3 KB, 5 KB, that is the limit for that segment. So for each segment, we have a base register and limit register. This information will be stored in the segment table, and segment table itself is in the memory. Okay, whose address will be given by STBR and whose length is given by STLR. How to provide protection? Like if I don't want to allow my process to access the address outside of its space. Now 2 things are there. Number 1, we need to check if the correct segment number is there or not, and that condition we already saw. Yes, if S is the segment number, it should be less than segment table length register, that is STLR. So that is one check. Now if I found the proper segment, then I need to check the offset with limit. So always remember, the segment number will be checked against STLR and offset will be checked against the limit or whatever the size for that segment. In addition to this, each entry in the segment table will have some sort of validation bit. We'll definitely see an example on this validation bit. And if this validation bit is equal to 0, then we'll treat that as illegal segment. Why it is so? Because maybe we have a different segment, but that segment is not yet loaded, because this allows us to start execution of program before loading all the segments. Just we'll mark it as 0, that means illegal segment. If there is an illegal segment, definitely will result in some sort of trap, and then operating system will catch it. It will bring that segment into the memory, and then it will check. Even read, write, execute kind of privileges are also possible. So we can provide some sort of permissions. That means segments can be shared. Okay. So typically code sharing is possible. So for example, if you are running multiple copies of the same program, and if there is a function, whatever the code part of that function can be shared by multiple processes of the same. Or you can imagine something like square root function used by 10 different applications, 10 different processes. We'll have single square root function loaded into the memory, and that will be shared between all the processes. That thing is only possible because square root function will be available in a separate segment, whether you are allowed to execute that or not. Okay, so that can be given with the protection bits, read, write, execute kind of protection bits. Now we saw two different types of problems when we looked after contiguous allocation. One is with fixed partition and one is with dynamic size partition. Now because segment itself vary in lengths, all the functions or all the logical parts of your program are not equal in length. No. So the segmentation architecture is having dynamic storage allocation problem, and that we have saw. There is a problem of fragmentation. Anyways, we saw solution for that also. That is compaction. In case of disk, we call it as a defragment. Okay. Let us see the segmentation example. See here. CPU generates the logical address. So this is my logical address having two parts. So this is logical address. This will have two parts. S is mentioned there, and this S is nothing but segment number, and D stands for offset. Displacement, that is the words, that is the reason why D is coming there, but that is an offset, right? Now there is one pointer which points to this one, segment table base register, STBR. So this is the segment table in the memory. Okay. So for each and every process we'll have STBR. Now whenever CPU generates some sort of logical address, it will be divided in S, that is the segment number, D is the displacement, that is offset. Now it will consult the segment table. Now this segment number will be used as an offset in this. See it here. What is length of this? This length is given by segment table. This length is given by total length, I am saying. Segment table length register, STLR. Definitely, first thing we need to check is whether S is less than STLR. If yes, if answer to that is yes, then what we'll do is we'll consult the entry for that particular segment. So what is the limit register for that and what is the base register for that? So for example, one segment is of size 2 KB, for example, and if the displacement itself is something like 3000, that is wrong. Because if I say the size of that segment is 2 KB, maximum offset is 2000. Or now talking in terms of multiples of 1024, maybe I can say 2048. So definitely 3000 is wrong thing. Okay, so that means once we consult the entry for that particular segment S, we'll take limit register part of out of that, and we'll check that limit with displacement. So here the condition is the D, that is the offset D, should be less than limit. Okay, if this is true, then it is valid address. If this is false, this results in addressing error. This results in addressing error. Got it? Now once this is true, we can generate the physical address by adding this base into the displacement. So this gives me base register plus displacement, that is offset D. So D plus D. How I got this D? We got it from the segment table, for which the segment number is used there as an offset. Any doubt in this? Any doubt in this? If you have any doubt, ask me. Or let us see one example. So let me share the whiteboard. Now let us assume that this is one segment, next segment, one more segment. I'll take some. This is segment number 1, segment number 2, say segment number 3, and say this is segment number 4. This is segment number 2, this one is segment number 3, and segment number 4. So there is one process. Let us assume that there is one process who is having 4 different segments. So these 4 segments are given there, right? Now what will happen in case of segment table is, again one more thing we need to assume about the size. Let us assume segment number 1 is having 600 bytes. Segment number 2 is having some sort of say 250 bytes. Segment number 3, let us assume 1480, 1480, and 4th segment is having some sort of 980, something like this. So segment number 1, 600 bytes. Segment number 2, 250 bytes. Segment number 3, 1480 bytes, and segment number 4, 980 bytes. And now let us assume this is my physical memory. This is my physical memory where segment number 1 is loaded somewhere. Let me make use of this tool. So this address is, let us assume that 248698. So this is the starting address for segment number, let us assume 1. Okay. Segment number 2 is somewhere 120098, something like this. Assume that this is segment number 2. Okay. Segment number 3 is somewhere here. Let me select randomly 168754. Here, suppose segment number 3 is used, and segment number 4 is somewhere here at the beginning, maybe. Let me use some address, something like 8244, something like this. This is segment number 4. Now, what is meaning of this? This is very, very important. Okay. Now, what I mentioned is segment number 1, whose base address is 248698. That means first byte of segment 1 will be at the address 248698. Second byte will be 248699. Third byte will be 648700. Likewise, 600 bytes will be from this address. So 600 bytes here, 250 bytes here, 1480 and 980, something like this. Now what operating system does is it will create one segment table in which we'll have something like this. Let me call this as on the top the segment number. Actually, segment number is used as an index there, and then we have two things here. Let me make use of this line. How many entries will be there in this segment table? It's very simple. 4 entries will be there, and these numbers will be like, let me use segment number 1. Actually, this number starts with 0, but because I use 1, 2, 3, 4, let me select those only. 1, 2, 3, 4. So these are 4 segments. Okay. Now, segment number 1. First of all, let me write down the value of limit register here and then base register here. So for segment number 1, the limit register will have 600. Segment 2, 250, 1480 and 980. Now it is becoming difficult for me to type in here, so let me type somewhere else and then move it. So 600. Second segment is 250. Third one is 1480. And segment number 4 is 980. Getting it, no? And then the base register is, as I mentioned, segment number 1 is where? 24898. Sorry, 248698. 698. Second one is 120098. Third one is 168754. and fourth one is 8244. So what I'll do is we complete it. Segment number 1, the best is something like this. Segment number 2, segment number 3, and segment number 4. You're getting it? How I get the segment table? So on the left, I mentioned this is the program in which 4 segments are there. I mentioned size of each segment, and this will be loaded into the memory at different places. Not necessarily contiguous, not necessarily in order 1, 2, 3, 4. It is random. Like for example, initially S4 is there, then S2 is there, then S3 is there, and then S1 is there. Okay. Now suppose the CPU want to execute some instruction somewhere here, and these instructions start with 0th address, and let me use some value there. So for example, total is 1480. Suppose it want to access the instruction at the offset 572. Now what will happen is, or can anybody tell me what will the physical address? Anyone? Looking at the previous, let me go back to the presentation. Have a look at this. Okay. First of all, we need to check if the value of F is less than STLR, that is the segment table length register. Find out appropriate segment number. You will get 2 values, limit register and base register. Check the offset. It should be less than limit register, and then base register will be. So for example, in my case, whatever the example I mentioned, CPU generated address S, D, segment number and displacement. So for example, segment number is 3 and displacement is 572. My question is it legal address and what is the physical address? Anybody? Just do calculation quickly. So very first thing we need to find out. Let me make use of sort of highlighter. Okay. Very first thing is this 3 part. This is the segment number. So definitely I'll go here. Right? So I'll find out the segment number. Now from this segment number, I'll get the value of limit register, that is 1480. So the condition I need to check is whether 572, let me use different color. The very first condition is I need to check whether 3 is less than segment table length register, and in my case it is 4. So in my case it is 4, right? So yes, this condition is true. Then I need to check whether this 572 is less than limit register, that is 980. And this is the limit register for 3rd segment. Remember, this is the limit register for 3rd segment. If this condition is true, yes, both the conditions are true. Then I need to calculate the address as the base register for segment 3, which is 168754 plus offset. This offset is 572. And if you do simple mathematics addition, you'll get the answer. It is 169326. 4 plus 2 6, 5 plus 7 12, 7 plus 8 12 plus 1 13, 8 plus 1 9, 69. So it becomes 169326. I think somebody has mentioned it on, is it? Yes, 168754 plus 572, that is 16. Exactly. Sakshi, 100% correct. So that is the way how we can calculate the physical address making use of segment table. And remember, for each and every process there will be segment table. Now for this process, assume this is process 1 P1. So very first thing is how P1 will get the segment table. Yes, that is through STBR, segment table base register, STLR, segment table length register. Is that clear? Anybody have a doubt? Neil Joshi, is it okay? Okay, Neil Joshi asked the question, what is this? What is value of STLR? See, STLR stands for segment table length register. Segment table length register. That gives you how many entries are there in the segment table. I already mentioned one entry in the segment table will be one segment. Now in this diagram you can see there are 4 segments. So STLR will have value 4. Segment table length register, even it is mentioned there. See here on this slide. This indicates number of segments used by a program. Can you see this on slide? This indicates number of segments used by a program. That is STLR. That is size of segment table in short. Is that okay? Yes, others, anybody has a question? 95 participants are there. Okay, fine. So we'll stop here. Next lecture we'll start with 8. Okay.